Hi, now let's continue to look at a different model, which is MD1 model. So in this case, we are using D in the middle because the service process time is constant rather than unpredictable or exponential. So it's a MD1 model. Some service systems have constant service times instead of exponentially distributed times. When customers or equipment are processed according to a fixed cycle, as in the case of an automatic car wash or an amusement park ride, constant service rates are appropriate. Because constant rates are certain, the values for and W are always less than they would be in the models we have just discussed, which have variable service times. As a matter of fact, both the average queue length and the average waiting time in the queue are halved with a constant service rate model. So if you look at the formula itself, you see the average length of the queue was reduced or halved, it divided by two, meaning shortened twice. And the same with the average waiting time, it was divided by two. And average number of customers is L plus LQ, right? So which was divided by two plus lambda over mu. So everything was just halved by two because of this impact. Now let's take a look at this new case, which is Garcia Golding Recycling Incorporation. Garcia Golding Recycling Incorporation collects and compacts aluminum cans and glass bottles. The trucks arrive at an average rate of 8 uh, trucks per hour. So that's a Poisson distribution, which is familiar with us. Truck drivers wait about 15 minutes before they empty their load. So that's a 15 minutes of wait time there. And drivers and trucks cost about $60 per hour. That's a waiting cost, right? And a new automated machine can process truckloads at a constant rate of 12 per hour. So they are considering, adopting this new automated machine system, and they can constantly process a truck at a rate of 12 per hour, right? So you can convert that to minutes, or one over 12 per hour would be another thing that you can use for your data analysis. And a new compactor would be amortized at $3 per truck unloaded. So that's a new cost for amortization of a new machine, right? It happens in accounting. So these are the information that we have, and given this information, we want to apply the set of formulas that we have learned from the previous slide and apply it to in this case. And this is going to be the calculation. The current waiting cost is 1/4 hour waiting time, right, which is 15 minutes times $60 per hour cost right here. So that's a waiting cost. So it's about $15 per trip is being wasted at this moment. And the new system that if we adopt, the lambda is now it can handle 8 per hour, so 8 trucks per hour arriving. So that's a Poisson distribution. And mu is constant, so 12 trucks per hour it can be processed. And average waiting time in Q, then if we use that formula from the previous passage, then WQ equals 1 over 12 hour. So that's given there. And waiting cost trip with a new compactor will be 1 over 12 hour wait times $60 per hour. Then it gives about $5. And savings then with the new equipment would be, it used to cost $15 per trip, now only $5 per trip, and that's a $10 per trip of the saving that we have. And cost of new equipment, if we subtract this $3 because it says that it is amortized at $3 per truck unloaded. So you have to subtract $3 from 10, then it gives you $7 per trip. So you can save about $7 per truck, and for an hour you are serving 12. So per an hour, how many? $84 per hour you can save. And if you are operating 8 hours, then it's going to be even more uh, profit or savings than before. Now let's do this calculation together using Excel.